My name is Mohammad Abdellatef. I'm a lecturer in Civil Engineering Department. This is my email. And this is my office. If you have any questions, please feel free anytime. Okay? Send me an email, send by mail. Okay? And good luck on that exam. Okay, so concrete is a material that we use in most of our structures, and we use it to design specific set of sections. We use it to design beams, we use it to design columns, and beams and columns, so beams and columns have a common section that we call beam column, and I'm going to explain this. So beams are usually members are subjected only to bending, which mean moment. Columns are part of structure that's only subjected to axial loads. So we refer to them in the concrete walls as beam. Beam column structures have both moments and axial loads at the same time. So when we design them, we have to count for them having both moment and axial load at the same time. We're going to learn how to design beams, how to design beam columns, how to design columns. Also, beams has something else that occurs on them that is called shear, and we refer to it as letter V. So we're going to learn to design 4 things: beams, bending, column, axial loads, beam columns, bending and axial loads together, and shear. To start, this is what we need to know to design. So for beams, when you look at a concrete beam, it typically looks like this. We have a cross-section that is rectangular. We refer to the width of the beam with the letter P as in breadth. This total height, we give it the letter H. And we have in beams reinforcement. Some people draw it like this, some people draw it like circles. It's pretty much the same thing. And the moment that is being resisted by the section, you can draw it like this. It's causing tension at the bottom side and compression at the top side, and the seal is on the side of the compression. To give this full notations, again, this is moment M, and we give the seal ES as its notation. And this distance here is very important, is what we call the concrete section depth, and give it the letter D. And we don't deal with, when we design, as you will see in the equations, we don't really care much about this total height. We care about this depth from the top fibers to the steel. This usually is referred to as the cover, and in some textbooks give it the letter D prime. And this is in the order of 2 to 4 inches. And if you take reinforced concrete here, we have calculations to do it. In the FA exam, it's not worth it to go in deeply in how to calculate this. If you pick 3 inches, you'll be on the safe side. You'll be fine. Okay. So what we want to understand is what is the capacity of a section like this. So if I know what is my area seal, if I know what is my depth, if I know what is my breadth, what is the moment capacity of this section? To do this, we kind of have to look at the stress and strain distributions, which again quickly, they look like this. So this is the strain distribution. So here we have the most famous number in concrete, which is 0.003. This is referred to as Epsilon C, the strain of concrete incompressive when it's starting to form. Okay, it goes linearly until we reach the neutral axis here. So this one is the neutral axis, and this distance is given the letter C. So the depth of neutral axis is 4, and then the remain strain profile is still linear. It can go to anywhere, that's fine, but this is the important strain that we need, which we call epsilon S. This is the strain in the seal. So if you want, you can always find what is the strain in the seal based on the strain in the concrete and this height C. And there are a few problems that I have some samples on here, is asking you what is the strain in the seal knowing some information. Okay, so we're going to use this in some problems. Now, parallel to this, there is a stress distribution, which is simply what are the stresses in this section. If you recall or not, concrete does not carry any tension. We don't design it to carry tension. It's very poor in tension. So we will have only stresses in the compression side. The compression side, I mean, is this part. And there is a lot of complication on how this compression stress distribution looks like, but we simplify it to just a plot, that's namely called Whitney stress plot, where the value of this stress here is 0.85 Fc prime, where Fc prime is the strength of the concrete. And this height here, we give it the name A, and I know the name's getting a lot, but in the equations that you have, all these letters would be provided. So it's just to know where they are. And this A is actually related to this distance C, such that if you know one, you know the other. By this equation over here, you can see it. Where is it? Here. A is equal to beta 1C. So A is equal to beta 1C. And beta 1 is 0.85. So A is roughly 85% of C. So if you know C, 85% of is this distance A. But what is important, if you calculate the volume of this plot, note this is a plot in 3D, is going to give you the compression force in concrete. So the compression force in concrete, C, is equal to 0.85 Fc prime, so this value, multiplied by the height A, multiplied by the width of the section. So this is what makes this cube a volume in this case, like this one, multiplied by the width. Now, if you think about it, this section is not at equilibrium by any means, because it has only one force in it. There must be another force that makes it at equilibrium, which is simply the tension in the steel. So we have a tension force in the steel T. And this is very simple. The tension force in the steel is simply the area of the steel multiplied by the yield stress of the steel. If you take a concrete before, that's why I asked, this is an approximation because it's not always a field, but for the sake of FE exam, we look at only sections that are controlled by the yielding stress. And to be in equilibrium, this here has to be equal to this here. So these two are equal. And this is the first equations that we have in bending, and in most of the problems that we will solve, you will find us looking at this equation to find what is the value of A. Since in most cases, you will be given the concrete type, you will be giving the concrete section dimensions, so P, you'll be giving the area of the steel, you'll be giving the yield, so you'll be looking for this distance A. Now, what I was looking for is the moment. So the moment is simply either of those multiplied by the distance between them, this distance over here. So the moment is simply the tension or the compression, since both of them are equal, multiplied by this distance. Now what is this distance? We know that this here is called D, and this is a rectangle, so this is in the half of the height, so this is A over 2, and this is A over 2. So the lever arm between both of those is simply D minus A over 2. So multiply this by D minus A over 2. And this is the second equation that we have in common. And if you have A, now we can plug everything in here, find the moment capacity of this section. We call this the nominal moment capacity, since if you go to lab and if you test, you will find that your section usually carries this value. But in reality, we don't design for this value because so many things can go wrong. So we add to it factor of safety. So we say that the ultimate moment that we can work with has to be a factor of safety, you call it 3, multiplied by Mn. And this is less than 1. In the case of bending, this is typically 0.9. In few cases and in few problems in the FE exam, you will be asked to evaluate a different value. Okay? And this equation over here, which you don't have to memorize, tells you that in the case of epsilon t is greater than 0.005, which in most cases, this is 0.9. But if epsilon t is less than that, this changes by those equations over here, such that it caps down at 0.65. I have a problem in the problems I have that is asking you, knowing this piece of information, find me what is the value of P. But if the problem doesn't ask you, you can safely assume it's fine. Okay? So this is, in just one slide, the review of what happens in Penning. Okay, any question about that? Perfect. So second, if we go back to this slide over here, what's happening? What did... Yeah. Okay. Second is beam columns, which is actually very simple since it's a graph. So in your FE exam material, you will be given a graph like this one. And I'm going to explain it. It looks scary. Maybe some of you saw it before, maybe not. But once you understand what's going on, it's very, very intuitive. So this graph, to be explained, has a horizontal axis that is value usually we call Rn, which is simply the moment applied on the section. Again, if I go back to here, we are discussing a section that has both moment and axial load on it. The moment applied on the section divided by Fc prime AGH. Fc prime AG is the area of the concrete section, and H is the height of the section. For some explanation on what's happening in here, if this is a plan view of the section, and I'm just rotating it by 90 degrees, I'm not doing a lot, and if this width here is P, and if this height here is H, what you will see is that on this section there will be both moment acting along H and an axial load acting in the center here. This will be. Okay. If I make a plan view, because I like the plan view more, yeah. Thank you so much. Yeah. If I look at the plan view, because this way I can visualize it as a column, so this is a column here. So you can have the axial load B and the moment M. So this height that goes along the moment is the height that we call H, and this one is P, and the area AG is the area of the concrete section. So AG is equal to P multiplied by H, as simple as that. Okay. There are other ones for circular columns, but we don't care about those. Not for the FA exam. Okay. So if I know the moment, and I know the concrete area, and I know the Fc prime, the concrete strength, I can find a dot here on this axis. Now this axis is usually referred to as Kn, and it's very similar. So this is Pn, the axial load, divided by the same thing, Fc prime Ag. So if I know the axial load, I know the concrete properties, I can find a dot here. And once you connect these two dots, what will happen is you'll find yourself between several lines. Each of those lines has a value of what we call reinforcement ratio rho. So if you can just look in, I know that it's very harmful to your eye probably. So you'll see that this one here has a value here is 0.08. This is this row, which I'm going to explain, is equal to 0.08, 0.07, etc. But you will find yourself, this dot is going between two rows, two different values. So let's say this is 0.08, and let's say this is 0.06, and let's say this is 0.04. So in this case, the values that I'm looking for, just by interpolation, is roughly 0.05. So what is rho? Rho is simply the area of the steel in the section divided by the area of the concrete. So what's happening here in real life? You would be given a section without reinforcement in it, and asking you, if I know what is the load and the moment, how much steel I can put in this section to make it stand. Okay? And in beam column sections, we put the steel in both sides, not just on the tension side. So this is going to be ES divided by 2, and this is going to be ES divided by 2. So half the steel here, half of the steel here. So the problem is going to give you two pieces of information asking for the third. As we will see, some problems going to give you the moment and the load asking you for the reinforcement. Some problem is going to give you the moment and the reinforcement asking you for the maximum load they can put in. Some is going to give you the axial load reinforcement asking you for the moment. So always about this triangulation between this value, and this value. For complete picture, you will see arrows here going out. Each of those arrows has a distinct value, which again you can see over here. It's E over H. We know H was what we don't know what's E. E is the eccentricity of the load, and just in a very simple term, E is the moment divided by the axial load. This in some problems is going to show up, but again, it doesn't create any complexity, just extra piece of information. Okay. So this is generally how we design beam columns. Questions about this? Good. Okay. So the third in line, which is much simpler than this, is columns. So in reality, every section can have both axial load and bending on it. But in practicality, we can ignore pinning on some sections. The code tells us that if E over H is less than 0.1, we can ignore the pinning. What does this tell me? That E is less than 0.1H, which if you recall, if I pull this back over here, E is M over P, so M is less than 0.1, so M is less than 0.1 HP. So M is very, very small comparing to the axial load and comparing to the section property. So if the moment is very, very small, and this is what we mean by the moment is small, we can ignore the moment completely and design the section as if it's a column. And in case of the column, it's just one equation, this particular equation, that P is equal to 0.85 multiplied by 0.85 also, FC prime, the area of the concrete, so this is AG minus AS, plus the yield of the steel multiplied by the area of the steel. There's another version of this equation. Simply if you take out AS as a common factor, it looks like this. So it's going to be 1 minus AS divided by AG. I'm sorry, we're taking AG out. But we call this before rho. So 1 minus rho plus F yield multiplied by rho. Both of those are exactly the same thing. Okay. What we will be given in here is either you'll be given the concrete section and the steel and SP, what is the maximum load that this section can take, or giving you the load and the concrete section and asking you for the steel. So pretty much one equation you'll be asked for one unknown. Now there's something that I skipped, but it's time to mention in here. So if you recall, when we went in here, we said there is a factor of safety that is 0.9 in the case of pinning. This is only in the case of pinning. In the case of columns and beam columns, the factor of safety P is much less, it's 0.65. And it's common in both of those. So when you're asking yourself, this is Pn, what is P ultimate in this case? Is simply this phi multiplied by Pn. So if you want to design this, in real life, you're going to assume it takes only 65% of this value over here. And the reason is, we know more about pinning than we know about axial load and shear. And the pinning failure is usually what we call ductile failure, which means, in simple terms, if this surface would start to fail, it's going to have more time, we can see it failing, so that we can evacuate the building. But when a column fails, it's usually catastrophic. It snaps like almost like a palm. You hear a very loud noise, it collapses, the whole floor collapses, you don't have time to run out. So that's why we are more relaxed in terms of the factor of safety with pinning, we have 0.9, but we are more strict in the factor of safety of axial load, so we have 0.6. Okay? So this is the simplest way, as you can see here, to design columns. Now, the last part is how to design shear, which is involving some steps. But if you kind of program your mind, you can easily navigate the shear problem. So what's happening in here is, if you look at a beam, and on this beam there is a uniform load, W. Now, if you recall, the bending moment looks something like this, and this is what we're designed for, and the shear force looks something like this. So we have a shear force distribution where this is the shear that we're designed for. We want the section to carry this shear here and here. The way we do this is we have a rectangle section. This is the same section, but the shear reinforcement is a set of stirrups that we put in this section line. So those stirrups has a specific cross-sectional area, let's name it AS, and has yield properties, FY. What is happening is, if you look at this diagram again, you will see that there are some regions in the concrete sections that has almost no shear. It doesn't make any sense to have stirrups in a section that doesn't have any shear. Okay? You don't need it. There's no shears, there's no need to reinforcement. So the code tells you that if you look at the value of a shear at a certain section, and this value of the shear is less or equal to the capacity of the concrete in shear, which we give it the letter VC, multiplied by phi, divided by 2. So half of the shear capacity, you don't need stirrups. So no stirrups here. So if your ultimate capacity of your demand is less than half what the concrete can carry by itself, do not even think about putting shear reinforcement. What is this VC? Again, you will find this in the notes that you will be given in the FE. This is the equation for VC. It's the width of the section, the depth of the section, multiplied by the square root of epsilon. What if it's greater than that? Okay, if it's greater than that, if it's greater than half of the concrete can carry, but still less than what the concrete can carry, so your section can carry it by itself, we say we are going to put the minimum stirrups. Okay, so the minimum reinforcement possible. And the minimum reinforcement possible, usually you are forced to use a certain cross-section. So what you are only left into choosing is the spacing. So if we look to this from the side, those stirrups are spaced like this. So as a designer, it's up to you to find this spacing as. And this table over here tells you, if you are in this case, where your shear is between half of the concrete strength and the full concrete strength, this is the spacing you're going to choose. It's simply the area of the stirrup multiplied by the yield stress divided by 50p, which is, this is BW or P, and one of these values. So the smaller of these two values. Okay, but make sure, because you can also go into a section that is almost at the edge here, you just, after VC over 2, this spacing cannot be larger than those distances here. So the maximum permitted spacing is half of the section depth, or 24 inches. So what you do is, if you are in here, you calculate this, these two, take the smaller of those, and make sure that you are not exceeding the smaller of these two. Let's say that you are exceeding now. So let's say that your V ultimate is exceeding phi VC. Now you have to put shear reinforcement, because the concrete by itself cannot carry this. Okay? The shear reinforcement Vs is simply V ultimate divided by phi minus VC. So simply what you have minus what the concrete can carry. So if you know what is this Vs, based on the V ultimate and VC, you can go and substitute in this equation over here, which is AS F yield E S. What? Yeah. And this is going to give you what is the spacing that you need. So you're designing for the spacing. So if your V ultimate greater than VC, what you will do is you will calculate what's the VS, how much shear you want your stirrups to carry, plug in this into here, and find what is the spacing that you need. And also there is a code requirement that this spacing has a maximum permitted value. Usually you don't hit this, but just in case, it's d over 2 over 24 if you are in this category, or d over 4 and 12 inches if you are in this category. So this is how to navigate this table. If you can navigate it, which I think you can find this spacing. Okay. So these are the 4 major design criteria that we face in concrete design. Again, moment, shear, columns, and okay, that's roughly 20 minutes. Perfect. So let's jump into examples. So how we divided those, as I have first some pinning examples, some beam columns examples, some shear examples, and some column examples. Okay. So let's go here. So this is the first example. Can you see this? Yeah. You'll have the slides, so that's fine. So in this example, we are given a concrete section of a width of 12 inches. Note that the height here is 21.5 inches, and this is the reinforcement. We have 40 parts, each of those of a diameter number 10. And I don't know if you recall, this number 10 is 10 divided by 8 inches. Okay. So what we want, let's use the problem. The problem is saying, according to the code, what is the value of P that should be used in computing the design moment for PMN for this particular section. So if you go all the way back to the first slide, I told you some problems not going to ask you for the moment, it's going to ask you for the value of P. And we are looking for this, if I go all the way back, we're looking for those physical equations. What is the value of P? And the only thing that is controlling what is the value of P here is the strain in the sea. So what we want in reality in this problem is the strain in the sea. That's it. So to do this, if this is my section again, and this is my reinforcement, this is here the neutral axis. This is the strain profile. So this is 0.003, this is C, this is D, and this is epsilon. So if I can solve this geometry, I simply find what's epsilon. So how to do this? Well, if you look at this triangle over here, this divided by this is equal to this divided by this. So 0.03 divided by C is equal to epsilon T divided by D. I'm going to sub directly since I know what is the value of D over here. The value of D is 21.5 inches. So if I know what is my value of C, oh, that's D minus C. So E minus C. If I know what is the value of C, I know what is my epsilon T, and I can sub in the equation. But if you recall, I told you the equation that we usually use to find C or A is simply the equation of equilibrium between the compression forces and the tension forces. So if I go in here, I'm hoping, and this is a correct hope, to find the value of A, and from it we can find the value of C. So let's plug this in here. The first equation, which is T is equal to C, tells me that 0.85 FC prime P multiplied by A, this is the C part, is equal to AS multiplied by FP, and this is FP. So I know what is FC prime. The problem tells me that FC prime is equal to 4 KSI yes, this is 4 KSI. This P here is 12 inches. A is an unknown. AS, if you go to the tables, you'll find a table that tells you what is 4 number 10 have, it's 5.09. And the yield stress of the steel is here, 60 KSI. So the only thing that is unknown here is A. And if you solve for A, it's going to be equal to 7.47 inches. And we know that A is equal to beta C, and this is 0.85. So from here, we notice the value of C. And it's going to be 8.8 inches. And we can take this value here and go all the way up here to find what's my epsilon. And if you do this, you'll find that your epsilon T in this equation, or in this case, is 0.004333 inches per inches. It doesn't have any. So this tells me that if you plug this in here, you'll find that the value of phi is 0.84, and you can choose it. So this is a roadmap of how to do this. We started by knowing that I need epsilon T to solve for phi. Epsilon T comes from this triangle. I need C. I go here in the first equation of the equilibrium here. I find that I get C. Okay? So this is the first example. The second one, which is has some similarities of it in terms of how we're going to solve it, it says we have this reinforcement section. You can see over here. Both those figures are the same. That is subject to a factored moment. M ultimate is equal to 49 or 94.8 kips. Note that this is M ultimate, not the nominal moment, so we're going to use a factor of 6. For Fc prime is equal to 4 KSI, and for yield of stress in the steel is equal to 60 KSI. And we are using 8 bars on 2 rows, so 4 and 4. Each of those are number 8, so that's 1 inches in diameter. And they are positioned, as you can see over here. It may be assumed without verifications that phi is 0.9, and most of your problems that doesn't involve calculating phi are going to be using phi immediately to 0.9. What is the maximum adequate height h to nearest whole inch of this beam? No, prep. What is the maximum? Oh, P. Yeah, what is the maximum prep P? So, what is the value of P? If we know everything about the problem, and even we know this height over here to be 30 inches. And here's my step on 2 lines. So this problem is the other way around. You have everything, even you have your seal, but you don't know what is the width of your section. So there are 2 ways to solve this problem. You choose whatever makes you more comfortable. The first one is, I'm going to go back to those equations again, but what I will not know is not the area seal or A. I'm going to be easily getting those, but this is going to be my unknown. So I'm going to try to set up the equation this way. Okay? So let's do this. We know that T is equal to C. So that is AS, which we have. We have the area of 8, number 8. If yield, which is 60 KSI, is equal to 0.85 Fc prime P, which we do not know. Okay, so this is unknown. Multiplied by A, which also is an unknown. But we have another equation, which is the equation of the moment in this case. This one. So the moment is equal to either the tension or the compression. I usually like to use a tension since it doesn't involve all of the unknowns that we have. So it's going to be PS that we know, F yields that we know, multiplied by D's that we know, minus A's that we don't know over 2. So now you have two equations in two unknowns. The easiest way is to get A from here. So A is going to be equal to AS F yield divided by 0.85 FC prime P. And take this, plug it in here. And the only unknown that you will have is omega. And from here you can find what is P. This is one way to do it. Although in the heat of FE exam and you have so many things to do, you might not see the line. So there is another way that to see the line and solving this problem is, I'm used to solving problems when I know the depth or I know the breadth. So what if I take this breadth and try it and find what is the moment? So one way to do it, if you are in autopilot mode, take this as your breadth, try it. Is it going to give you this moment over here, which is, where is the value of the moment? Yes, is it going to give you the value of the moment over here, which is 648? Maybe yes, maybe no. If it gives you the value, then you're in luck. If it doesn't, go try the one after it, and so on. So this way, yes, you are solving the problem 4 times, but probably you have your equation set up, you're just changing the numbers. So based on your mindset in the FA exam, this might be the shortest line, but picking each of those and trying them independently might be an easier way to do it, although it's more time consuming. Okay? Both of those are valuable. So some things to note here. What we are using is Mn, if you recall, here, which is simply M ultimate divided by P. Okay, so here you have M ultimate divided by P. This is something do not forget. Something that I do not specifically like about this problem, although it's 100% true, I would use it if I'm designing in an actual problem, in actual case, is you are given the shear reinforcement here, and you are trying to find the depth from the top fibers to the middle point between the shear reinforcement that we defined as D. And the problem jumps through a lot of hoops to estimate what is this distance over here. And after a lot of hoops, after jumping through a lot of hoops, it finds out that this distance is 3.5 inches. Okay? If you take the same problem and solve it only with 3 inches as an average value of D, you will be very close to the final answer. So if you have time, you can try to read this and calculate what is the value of this part over here, which we call the cover. But if I'm doing the FE exam, I'm not going to spend this much time. Probably have more, my time is more valuable. I have more problems to solve. So this 1 minute may give me 1 minute another problem that I need. So in any problem in the FE exam that involves pending, you can immediately take this distance as about 3 inches. And it's going to be very difficult. Okay, pseudos is going to save you. So this is the second problem. It's a different kind of approach, but again, we can look at it from the same approach just by trying this one. The third problem here is we have a flexural design case. Again, you are giving the depth immediately, which is 20 inches. The width is 16 inches, and we are giving the reinforcement to be 4 number 8. And the problem is asking you what is the moment capacity of this section. So this is pretty much a straightforward problem. And actually, I should have started by this one, thinking about it. So we're giving the depth, the width here to be 16 inches, and this distance here, D, to be 20 inches. This is the steel. This is 4 number 8. And if you go to the tables, you'll see that 4 number 8 has a value of 3.14 inches square. And you are given what's your FC prime, and it's 4 KSI. And you are given what's your value of F yield, which is 60 KSI. So this is pretty straightforward to what we learned in pending, which in first find A, second find the moment. So let's do this. First, you're going to always start by this equation, always, that the tension in the steel is equal to the compression in the concrete. So AS that we know multiplied by F field that we know is equal to 0.85 FC prime that we know multiplied by B that we know multiplied by A that we don't know. And from here you can get the value of A. And the value of A in this case is going to be equal to 3.64 inches or 46 inches. And then jump straight into the second equation, which is M is equal to either of those, so T or C. Again, I prefer to use T. It's much cleaner. Multiplied by D minus 0.2. So this is AS multiplied by F field multiplied by the depth, which is 20, minus A, which is 3.46 over 2. So it's going to give you what is the nominal capacity, and then the ultimate capacity, which the problem is asking you, is phi multiplied by Mn. And again, without questioning, you always use phi equals to 0.9, unless the problem specifically is asking for a different value. So this is the simplest one. Actually, I should have started by this one, because this one doesn't have any tricks. It's simply applying in the equation of bending just enough. Okay? So let's take a problem that involves this value of phi again, not directly, but just finding the strings. So this problem is saying there's a reinforced concrete section where FC prime is equal to 4 KSI and F field is equal to 60 KSI. And it's a beam, it's simply supported. The span of this beam is 25 feet. This is a lot of information. And the width of this section is 15 inches. So if we draw the cross section of this beam, it has a width of 15 inches. And the depth of this section, so D, until the steel, is equal to 24 inches. And we have reinforcement that is 4 number 10, so those are 4 number 10, which again you can go to the table and find the area of those. And the shear reinforcement in this case is number 4 at U shape, which again something you may use in actual design, and I'm going to tell you how, but I will not use it in this problem. So what's happening here is we have those stirrups I told you about. I'm going to draw them in actual thickness. So those are the stirrups. And then inside them there is a 4 number 10. So the problem is asking, what is the tensile strain in the steel? So what is epsilon T? So what is all of this about? You might ask. First of all, this is not necessary at all. This has not been used in the problem. There's just an additional piece of information. You're not going to use it. Second, the problem is telling you, although it's not clear, and that's why I don't like this particular problem, it named this as D, but it's not. This is not the depth of the section. This is actually what they call the depth, is the height of the section, H. And I think this is kind of misleading, because if you read clearly, you'll say that the section depth. This is actually not the section depth. And I think it's going to be clear. This is from a training book. This is a section height. Okay, so what is the 24 inches in this particular problem, in this particular book, is the height. But it's not named as height. Now, if this 24 inches, and we need the depth, which is from the top fibers to the steel, we need to subtract this height over here, this bar size of the stirrup, and half of the diameter. And if you go along those tedious calculations, which I have them in here, you will see that the difference is 24 to 21, 3 inches. So do not go through those. Again, your time is more valuable. 3 inches is roughly enough. Okay, so the depth in this problem is 21 inches. If we want to know the strain in the steel, it goes back to the same strain diagrams that we drew before. This is 0.003, this is epsilon t, this is c, and this is d minus c. So it's exactly the same as this problem over here. Yes, it's exactly the same like this problem over here. When we wanted to find the strain in the seal, we started by saying that the tension in the concrete, tension in C is equal to the compression in concrete. From this we find the value of C, and we find following this the value, well, we find the value of A, then the value of C, then we plug in here. So this is pretty much exactly the same like this problem 2 problems ago, except we end up at what is the strain in this. Okay. Again, be mindful that you don't have to do all of these calculations unless the problem is asking you to find what is the cover, and this is part of the problem, and usually it's not being asked. But if you approximate the cover by 3 inches, you can solve this problem very easily. Okay. Again, you plug in here, find what is the value of A and C, and then you go to the triangle relation to find what's it. Okay, so, and this is the last problem in pending before we move into beam columns. So in this particular problem, the problem states that we have a rectangular concrete section with a span 18 feet. Again, it might be relevant, it might not be relevant. And there's a uniform distributed load on it. So this is W ultimate is equal to 5 kips per feet. And the beam section is rectangular with a width of 12 inches. And a depth of 20 inches. And you're given FC prime to be 5 KSI, and giving what's F field to be 60 KSI. And the problem is asking you what is the required flexure reinforcement? What is the area steel that you need in this section? So if you look over here, you will notice that we don't have the moment. Not directly anyways. But we know, if you took strength of material class, that in a case of a simply supported beam with a uniform load on it, the moment is, again, if you recall, is W L square over 8. You recall this? Okay. So W is 5 kips per feet, 18 square divided by 8. This is going to give you the ultimate moment, which is 202.2. 202.5 kips. And Mn is equal to, M ultimate is equal to Pmn. So 202.5 is equal to 0.9 multiplied by Mn. And from here you can find the Mn that you want to design for. The problem here is we do not know AS. And this is kind of very similar to when we didn't know B. So you have 2 ways to solve the problem. The first is, again, to set up the equation, not knowing what's your AS, or, and this is what I like about this solution over here, you can try. You can take the first AS, plug it in here, and see what is the moment capacity. Does it meet what you need? It does? Okay, then this is your answer. It doesn't, then go back. And this is the simplest way to solve the problem. Just try the 4 of those in here. So again, based on what you think in the exam, you have time, you don't have time, you see the line of just solving the equations, or you don't see the line, so you can try them. Anyways, you're going to get to the same answer. Okay, so both of those are pretty common. So all of those are the 5 examples on pending. Do you have any questions on those? No? Okay. So we can move into beam columns, but I need to take a sip of water. Where's the nearest water fountain here?
I don't know.
You don't know. Okay, give me a minute. I'm going to find it, but I'm going to be right back. Okay. Okay. So again, this is the team column problems, and if you can, or if we can train well to read those graphs, it's going to be very easy. Those kind of problems, if you can just plug in correctly and read the graph correctly, those problems are the easiest ones. So let's read this first problem and try to understand what's going on. The problem says we have a load acting on a rectangular section, this section over here, with an eccentricity of 4 inches. So the eccentricity of this section is 4 inches. It doesn't matter to which side, both of them, we're dealing with eccentricity in absolute. And you are given what is your FC prime, which is 4 KSI. What's your F yield, which is 60 KSI. And you are also given the column dimensions, and it's very neat that here that you have the plan view along with the section. This here is the H, so this is the one that associated with the eccentricity or the moment. So this one here is 20 inches, so H is 20 inches, and P is 14 inches. And the problem is asking you for this particular case, and if you have in this section 8 repars here of number 10. So the AS is 8 number 10. Not few, 8 number 10. And if you go to the tables, you will see what's 8 number 10. I think it's, where is it? I think it's 4 inches square. I don't recall what is exactly, but if you go to the table, you will find what's the area of 8 number 10. As shown, what is the maximum factored load that we can apply to this column over here, and this column can withhold it? We have a problem here. If we recall, when we introduced this graph, what we wanted is, I'm going to give it here. What we ideally wanted is using the moment and the load, intersecting into a section, finding the reinforcement. Here's the problem is flipped. We have the reinforcement, and we're looking for this point to find from it the moment and the load. We know from just the setup of the problem that the moment is equal to the load multiplied by the eccentricity. So if we know the load, we know the moment. If we know the moment, we know the load. But still, we need to use this graph. It's kind of tricky now. How can we use it? If you look at the information that this graph is trying to plot, one of them is E over H. Okay? So we can actually define our section along one of those lines, because we know what is E over H. So E over H is equal to 4 inches divided by 20 inches, and which is 0.05. And if you go here, you will see that there is a line that is associated with this value of E over H, which is this one I'm having. So E over H is 0.2. So this here, if you look here, is 0.2. So anything along this line can represent our section. But any point along this line, this is too much to ask. Which point exactly? If you also look closely over here, you will see that we have the steel AS, and we have the concrete section, which is a multiplication of these two. So multiplying both of those is going to give you AG. And AS divided by AG is what we defined as rho. So if you do this, AS is equal to 8, number 10 has an area of 1.27 divided by 20 by 14. You will find this to be 0.036. And this is when you will have to do some interpolation. So we have here, this is 0.03, this is 0.04. So 0.36 is going to be somewhere between both of those. So now you have a point, and this point represents your section. And if you go sideways, you will see that this point is at Kn here equals to 0.9. But Kn is equal to P ultimate divided by P, Fc prime, Ag, and we know everything over here. So from here we can find the load. So you can see this problem is the other way around. I do not know the load and the moment, but I know the reinforcement and the eccentricity. And from these I can find this one or this one, which is going to give me the exactly same answer. Okay, so this is one way to read the graph. And let's go to another problem, which is going to give me two other pieces of information. So this problem is saying that we have a rectangular section, and this rectangular section is an 18 by 18 inches. So 18 inches by 18 inches. And we have reinforcement here and here. So it's kind of implied that the moment is going to go this way. If C prime is, you always be given in this kind of problem what is if C prime and what's the yield stress. If C prime is equal to 4 KSI and if yield is equal to 60 KSI. And we are being subjected, or this section is being subjected to dead load. T dead load is equal to 200 kips, and live load that's equal to 300 kips. And both of those, because we have a problem that's not exactly that, both of those has an eccentricity of 4 inches. There's another problem that I have here is that both of them has different eccentricities. So if this is the case, well, I know what is B. The ultimate load is 1.2 the dead load plus 1.6 the live load. I don't know if you've seen this equation before, but this is how we calculate the ultimate load from the dead load and live load. And this is going to be 720 kips. And the moment, the ultimate moment is equal to P ultimate multiplied by the eccentricity, which is going to give you what is the value of the moment. So the problem is asking you for AS. There's two ways actually to solve this problem. The way I portray here, which is kind of, I think this is the easiest way, is take this P ultimate and find what's the value of Kn, which is going to be 0.85. So draw this 0.85 line, and you can use one of these arrows, since any of these arrows is simply E over T. And you know that E is 4 and H is 18, so E over H is 0.22. So you can find what's 0.22. And then you can intersect here, find by interpolation what is the value of rho, which is going to be roughly 5%. Or if you don't like this, if you want to use the traditional route, we know what is the moment, so you can calculate what's Rn and go up from here and find also the value of rho. So both of those are going to give you exactly the same answer. If you want to use Kn, or I'm sorry, Kn and E over H, or if you want to use Kn or Rn, both of those are going to give you what is the reinforcement ratio. Now you take this rho multiplied by Ag, so rho is equal to As divided by Ag, multiply rho by Ag is going to give you what is the steel reinforcement that you need, which is 16.2 inches squared. Note that this 16.2 inches squared for both sides combined. So the problem is asking what is on each side is going to be Z. So read exactly what is the problem is doing, because in some problems they're trying to be tricky. But if you use the problem well, it's asking for the total steel or steel on one side. Okay? So let's jump to another problem. which is again very similar in approach. We have a short reinforced concrete column of a dimension also of 18 by 18 inches. And in this particular problem, we have total number of steel of 12 bars, number 10. Although the problem doesn't show this, it's not kind of accurate, but the steel that we have here and here combined is equal to 12 number 10. It shows just 1, 2, 3, 4, 5, 6. It shows just 8. But don't look at the graph. Look at the information that you're getting. And knowing that the dead load is equal to 400 kips, and the live load is equal to no, this is 220. The load is 220 kips, and this is 400 kips. And knowing that also Fc prime is equal to 4 KSI, and F field is equal to 60 KSI. The problem is asking you the other way around. The problem is asking, what is the maximum eccentricity, E, that you can have on this section? So how far you can put your load from the center? Is it 1 inch? Is it 2 inches? Is it 5 inches? How far this eccentricity could be. So let's see what piece of information that we have. We know off the bat what is my P ultimate. This is 1.2 the dead load plus 1.6 the live load, which again, if you look closely, is going to be 904 kips. We don't know M, we have no information about M. We don't know E, we have no information about E. But we know rho. Okay, so rho is equal to AS divided by AG. So the area of the steel is 18 multiplied by 18. So, I'm sorry, 12 multiplied by 1.27. So 12 repars, 1.27. And the area of the steel is 18 by 18. So rho here, if you would calculate it, is going to be equal to 0.047. So if you look at this graph, and I hope it's large enough, you can interpolate for what is the value of rho, that's 0.047. Okay, make sure that you are interpreting correctly. You're not just moving into 0.05. And from the load B, you can find what's your Kn. So now I know what is my load B, or from this I know what's my Kn, and I know what is rho. So I can intersect and go down and find what's my Rn. And if you do this, you'll find that your Rn has a certain value. Or, which I don't like this particular solution because of this, you can interpolate between these arrows over here. And the problem is doing this. The problem is interpolating between those arrows to find what's E over H. We found it to be 0.017. I don't like this because interpolating between these arrows involves the angles. So I really don't like doing this way. If I'm going to be solving it, I'm going to take this point, go down here, find what's my Rn, and from here find what's my moment, and using the moment I can find what's my eccentricity. Okay? So use the way that you think the easiest. I don't think this is the most intuitive way in the problem interpreting between the arrows. I think finding Rn is easy. Okay? Cool. So this is a very easy problem. It's actually easier than you think. So the problem is asking, what is the largest factor moment that you can apply on a section, in which case you can ignore the eccentricity, which means that this moment, if you have it, you will not have to jump into those graphs. Knowing that P ultimate is equal to 600 kips, and the column is 15 by 15 inches. And you have what's your Fc prime, 4 KSI, and what's your F field, which is equal to 60 KSI. So the problem is asking you, when can you ignore the moment? And when we started, we said we can ignore the moment if E over H is less than 0.1. This is when we said, okay, if it's larger, we're going to use this. If it's not, we're going to use just the moment equation. Which means that E has to be less than or equal to 0.1 of this, so 1.5 inches. Now, if E is less than 1.5 inches, then Mn is less than, or M ultimate is less than P ultimate multiplied by this value of E. So this is simply 600, and this is 1.5 inches, which give you 900 kips. So as long as your moment is less than 900 kips inches, or if you want to put it in kips feet, it's going to be 75, then you can ignore this moment, and that's it. So the problem is just asking, do you know this identity or not? Do you know that if E divided by H is, if it's below 0.1, then you can ignore the moment? If so, you can just find E, multiply this by P, find the moment. Okay, nothing more than that. Okay, so the following example, which I think this is the last example that we have in eccentric loading. Again, we have a cross-section that is defined as 16 by 12, and generously it's been drawn here to be 16 by 12. So this is H, this one that goes with the eccentricity, and this is B, this is 16 inches. And you are given what's your FC prime. So this one is 4 KSI, and you're given what's F yield, and this one is 60 KSI. The difference in this problem is, it says that you have a dead load, and you have a live load. And the dead load is equal to 300 kips, and the live load is equal to 180 kips. But the eccentricity of this load is equal to 0, and the eccentricity of this load is equal to 4 inches. So this problem is tricky just because of this line over here. Normally what we do is we say, okay, the P ultimate is equal to 1.2 P dead load plus 1.6 P live load, and this is going to be 1.2 multiplied by 300, 1.6 multiplied by 180. This is going to give you 648 kips. And then what we did in the previous problem is we take this multiplied by 80. So if I pull this from here, we took this, multiplied by E, we find the moment. But in this particular problem, we don't have one E. We have eccentricity for the dead load and eccentricity for the live load. So two eccentricities. So how do we tackle this? It turns out that you can easily think of it this way. From this, you can say, okay, what is the moment of the dead load? The moment of the dead load is simply P dead load multiplied by this eccentricity, which is equal to 0. Okay? What is the moment due to the live load? The moment to the live load is simply the P of the live load multiplied by this eccentricity. Let's call it eccentricity of live load, and this eccentricity of dead load is going to give you 180 multiplied by 4. This is 520. Is it 520? 0, 32, 720 kips inches. From here, that the ultimate moment is equal to 1.2 the ultimate dead load plus 1.6 live load. So this is 1.2 multiplied by 0 plus 1.6 multiplied by this 720. This is going to give you 1152 kips inches. So this is kind of the trick of this problem. Once you figure it out, the problem is straightforward from this point onwards. Those dead loads and live loads immediately give you the ultimate load, but to find the moment, you need to find the moment due to the dead load zone due to the live load, and then find the moment by itself. Okay? And if you are curious, the eccentricity in this case is simply M ultimate divided by P ultimate, which is 1152 divided by 648. It's roughly around 1.9 inches. Roughly. Now, after you know this and you know this, the problem becomes very straightforward because you can find what's your Rn and what's your Kn and intersect them over here and find what's your value of rho. One other thing this problem is teaching us is if you go in, you will see that this node goes inside the last envelope. And the last envelope is 1%. And this is the last envelope because at any given section, we cannot go below a reinforcement ratio of 1%. So if you find yourself needing 0.5%, it's not allowed. You have to add 1%. So the area scale in this case is simply 1% multiplied by the gross section, which is going to give you 3.2 inches. Okay. So again, the two tricks in this problem. The major one is each of those has different eccentricities. The other one is it's inside the envelope, so use the smallest envelope. Any questions about those? Okay. So I have one problem for columns, for pure columns, since it's just substituting in one equation. And let me find this over here. We have exactly one equation to substitute in, and I picked one problem because it's pretty straightforward. So we have a circular column, and this circular column is supporting a load of 300 kips of dead load. So P dead load is equal to 300 kips, and P live load is equal to 350 kips. So all loads are concentric, which means E is equal to 0, which means that we don't care about Mn. The longitudinal reinforcement is laterally confined by stirrups. We don't care about this one for FE, but we have two types of columns if you take concrete design class. But the only thing that we care for is this type of columns. And the FC prime for this particular concrete is equal to 4 KSI, and the yield stress of the steel is equal to 60 KSI. And the problem is asking you what is the maximum, according to ASI, reinforcement to be used. So what is AS? In this column based on this information. Okay. So you are just looking in every piece of information in this equation over here. If you can find them, you can solve the equation. Okay? So from here, we know that P ultimate is equal to 1.2 P dead load plus 1.6 P live load. So this is going to be equal to 920 kips. The equation is, if I put in phi here to this side and phi here to this side, this is going to become P ultimate. Okay, so P ultimate, which is 920, is equal to phi. If you recall that we said phi is a factor of safety in columns, and P in columns is 0.65, multiplied by 0.8, multiplied by, you can use either this version or this version. It's pretty much the same thing. Okay, this particular solution uses the row version, which is fine. Okay, so the gross section area of this is not known. Wait, which one is known and which one is not known? So our supported loads and loads of cars, the comparison. What is the? Oh, I'm sorry. It's giving you what is rho, and it's not giving you. Makes sense. Okay. Yeah, the problem is asking, and again, I misread the problem, but I have the solution correctly. If the maximum permitted ACI reinforcement is used, so if rho maximum is used, I'm going to give you what's rho maximum in a second. What is the cross-section of the concrete that we can use? Okay, according to ACI in columns, the maximum reinforcement that you can use is 8%. You cannot exceed this in any case. So you know what is rho, and this is why we use this version of the equation. and we don't know what is the area of the concrete section. So AG. So this is here 0.85, 0.85, HC prime, which is 4, 1 minus rho, multiplied by the yield stress multiplied by rho. And from here, the only things that you don't know, what is the area of the concrete section, which turns out to be 210 inches square, so the answer is actually B. And the problem might ask you for the diameter. So the trick of this problem, and actually this is why I put it in the first place, is you probably forget or don't know that the maximum reinforcement ratio that you can use in columns is 8%. The typical case of this problem is giving you the reinforcement, asking you for the cross-section, or giving you the cross-section, asking you for the reinforcement, or giving you the cross-section and reinforcement, asking you for the load. So just one piece of information that you usually do not know and are trying to solve in this equation. So I just picked one equation in column because I think it's easy, and I picked also one equation in shear just to demonstrate how to use this idea of the tables that we discussed. So this is a case where we have a rectangular section here, and this rectangular section has a width of 15 inches and a depth or a total height of 25 inches, and we have our stirrups here. And the problem says, what is the required spacing? And the shear problem is going to always ask you for spacing. What is the required spacing for this stirrups? If we use number 4, so this rebar here is number 4, which means has diameter of half an inch. In this beam, knowing that the ultimate shear, V ultimate, on this section is equal to 80 kips. So you solve your beam, you find at support what is the maximum shear, and it turns out to be, what's happening? Yeah, okay. It turns out to be 80 kips. And assuming that the cover is 1.5 inches and FC prime is equal to 4.5 KSI, and F yield is equal to 60 KSI. Again, I'm not going to go through the calculation to find what is the covered size. I'm just going to say this is 3 inches and use D equal to 22 inches. And this problem is going through the hustle of finding what is this depth. And again, guess what? It's 22.375 inches. So 3 inches is fine. Okay? So we look at this problem. We recall the following, that if we know, and let me pull this from here. If we know that the ultimate is less than half of VC over 2, then we don't need stirrups. Well, the problem is giving you stirrup spacing, but let's be hopeful. Okay? So first I'm going to calculate what's VC. So VC, based on the equations that you'll be given, is equal to this formula over here, 2 PD square root of FC prime. So 2 square root of FC prime, which under the square root we use the PSI virgin, multiplied by P, which is 15, multiplied by D, which is equal to 22. This is going to add up to 45 pounds, 45,000 pounds, so 45 tons. So is this less than half PC, where P is equal to 0.75? Absolutely not. Because VC divided by 2 is roughly, it's going to be roughly around 20 tons. So 80 is definitely clearer than that. Okay, second check. Is it less than VC? Okay, VC is 3/4 of this, so roughly what? Let's say 24, 25. Is this less than 80? It's less than 80. Okay, So we are not in between both of those. Okay, we're actually exceeding this phi VC. So actually, V ultimate is exceeding phi VC, which means that, okay, we will have to go to the same table. I'm going to scroll back just to the same slide. Okay, we were hopeful that we will not need any reinforcement. We did. We were hopeful that we will be here. It's not. So we will have to be here. The V ultimate greater than VC. So from here, we know that we need to calculate what's the value of Vs. And if I go all the way forward, here, yes. Vs, the amount that the shear reinforcement should carry is simply the load minus how much the concrete is carrying. Okay, so Vs is equal to Vc divided by phi, which is 0.75. I'm sorry, V ultimate divided by C, which is 0.75, minus Vc. And this is going to be equal to 61.67. And just plugging in the equation of the spacing, which is equal to As multiplied by F field multiplied by D, all of those things you have, divided by Vs that you just acquired, gives you a spacing of 8.7 inches. So this is something we have. This is from number 4 repar. This is, I think that's 60 psi. Yes, it's 60 psi. This depth here is 22, and this is a 61.67. So from here we get the spacing. We have to make sure that this spacing is not less than the minimum spacing. So we go to the second part of the table, which again, all the way here. We go to this part just to check that this spacing that we calculate in here is not less than the minimum spacing. Okay, and the minimum spacing is based on either we are in here or in here. And if I go forward all the way, you will find yourselves that you are less than 4x if square root of x prime PD, which means that your spacing should not exceed d over 2 or 24 inches, which is 11.2. But you are 8.7, so are not exceeding the maximum spacing. Okay, so the one that you're going to pick from here is the 8.5, which is closest to 8.7. So again, the roadmap to solve this problem is, I start with the problem. I have what's my V ultimate. Okay, I evaluate always first what's my VC. Ask myself, am I below half VC? Then I don't need anything. No. Okay. Am I below phi VC? So I need the minimum. No, I'm greater than that. So I calculate what's my VS, and from VS I find the spacing. The problem might go actually the other way around, which I tried to find a problem like this, but you can, if you dig deeper, I couldn't. You can be given everything, the spacing, the reinforcement, and asking what is the V ultimate. So you go the other way. You simply plug the spacing here, finding VS. You plug VS over here, and VC, finding V ultimate. So the problem can go the other way around. Okay. Let's say that you get puzzled in the exam. Try your alternatives inside the equation. Pretty much the same thing. If you every time you think the problem is trying to inverse the solution, try the solution. It's usually the easiest one. Okay, so I had 3 more examples just in case I have time, but I think this is not. I'm just gonna briefly skim through them and give you space for questions. So this one is for pending. It's pretty much straightforward. Having a depth, ASTL, finding the initial active depths, and from this finding what is the MN. So it's pretty much straightforward pending problem. And again, I'm gonna use the slides. And this one is an additional problem in shear. Still, it's asking actually it's the other pending problem, asking for how much moment that this section can carry. And this one is a beam column problem, pretty much the same thing, finding U over T and finding. Usually when I have more time, I go through those, but it's pretty much the same ideas. I'm just adding more of it. So, do you have any question about any of this or something else in reinforced concrete? No. Okay, I'm gonna hand these slides to Amelia. You can ask her, and she can distribute them. If you have any questions, just let me know. I probably should have introduced myself earlier on.